So good morning, everyone. So my name is Abhishek Dhar, and so I'll talk about random walks. So how many of you have come to the previous year's school? To that end, it's so basically I'm going to talk about random walks. More this side. Here. Here is it? Okay, so random walks is sort of the most basic non-equilibrium process. Okay, but it's really something. It's kind of a what I mean. It's like the harmonic oscillator problem in quantum mechanics, or the hydrogen atom problem. And basically, using this framework, you can almost understand any like stochastic process. So it's good to understand this in good detail. So, and it also is, I'll kind of use it to teach various techniques that are used in like non-equilibrium physics. Okay, so what are the things I'll talk about? So basically, many things about random walks. So basically, like the most simplest question is, what is the probability I'll be at some place? What is the mean square distance random walker travels? Things like that. So various properties of random walks. Uh, so and so many of this maybe you already know, but it doesn't harm to repeat. And then, so the basic, and then there's some interesting things related to this thing called the Polya problem. So this is related to the question of like, if you do a random walk, what is the probability? So you just start walking randomly. What is the probability that you will ever return to the starting point? So this is called the Polya problem. And this is related to various things like first passage distributions and so on. So I'll discuss this problem. Uh, and then, so this is also a framework when you can learn a lot of techniques. So basically, some definition of what a Markov process is. Markov processes. And so I'll give some examples of what is not a Markov process. And sometimes you can start with a non-Markov process and make it a Markov process. So this is a techniques like generating function methods. So this is really a very powerful technique. Okay, so in some sense, it's like doing Fourier transforms and Laplace transforms, but it's good to understand it in a general framework, and it will be useful in some of the lectures in the next 2 weeks. Okay, and then like when you talk of Markov processes, you write master equations and things like that. So I'll talk about master equations. Something called a W matrix, which is like the Hamiltonian of a quantum system. Okay, so W matrix in stochastic problems is like the Hamiltonian of a quantum system. And then in the last lecture, if I have time, I'll talk about linear response theory. So which is kind of different from random walks. Okay, so but okay, so I'm not sure I will have time, but in the last lecture I might do this. Okay, so let's start with random walk. So first, what I'll do is okay, so we'll first define the definition of model. First, I'll start with one dimensions. Okay, so basically, like you have a, so this is, I'll start with everything on the lattice. Okay, so everything, random walk is by, usually on, you define it on a lattice. So you have a one-dimensional lattice. So this is the origin, and you have points 1, 2. So this goes from minus infinity to infinity. And then you have some walker who might be let's say he's a drunk guy, and then he every time step he just moves randomly. Okay, so first step he takes like that, and then he tosses a coin. If it's up, he goes this way. If it's down, he goes right. So and then that's how he moves. So every step is a random process, which can be +1 or -1 with equal probability. So it goes like that, and then maybe like that, and then it might turn back, and then it might go here and go here, and so on. Okay, so every step is +or -1 with equal probability. Okay, so I can write, let's say after and in so n discrete time steps, right? So this we are time is discrete, space is discrete. So this I denote by y of n. Okay, so then this process, of course, is given by where Zn is a random number with, which can be +1 with probability half and equal to -1 with probability half. Okay. So this, if I write this is exactly equivalent to what physically what I described. Okay, so now. So given this random number, I mean, so for each step, this is the distribution of the step. Right? This is the step distribution, and this, of course, obvious property is in average is 0, right? And what is in square average? Huh? 1/4. Okay, how do we find it? I mean, what are the possible values it can take, right? It can take 1 with probability half, and it can take, again, if it's -1 also, it's again 1 with probability half. Right, so that's 1. Right, so that's n square is 1. Okay, so now, I mean, one question you can ask is like the simplest physical question of interest is after if you take n steps, then what is your average position on an average, right? So if you do it, I mean, once you might land right at the end, right? I mean, by chance you might just take all the steps to the right. So at most, of course, you will get go to. Okay, so after n steps. So it can be it can be at most at -n. I mean, in the least it can be at -n, or maximum it can be at n. And there is some probability that you are at various places, right? Okay, so now I can ask on average. So if I do it many times, on average, where will I be? Okay, so that's the simplest question. So x or what is y? So y after n steps, what is the average? Right. So this, I mean, it's easy to calculate. I mean, so this, what we note is that since using this, I can, okay, so this is what, so y at n. So if I just do this recursively, then it's clear that this is I, So n steps is just sum of n random steps. And so then what is yn average? This is since Zn average is 0, so this is 0. Okay, then we want to find yn square average. Okay, so yeah, so on average you are at 0. But of course, like in each realization, you won't be exactly at 0, right? You won't come back exactly with high. I mean, maybe with high probability you come back to the origin. But then you can ask on an average, like how much do I travel? I mean, like, I mean, maybe I'm going like this side equally probable and this side is equal probable. So it's like this. But if I look at the actual distance, modulus of the distance, then how far have I gone on average? So then one should look at the fluctuations in the distance travel. So I should look at yn square average. Right. So again, I'll basically use this. So this is given by sum over the n square average. So n equals to 1 to n. And so this is equal to, okay, so now this I break it up into two parts. One is, okay, so this summation is like sum over n and m. Okay, so now what is this? So, okay, so one thing is that each step is unrelated to the previous step. Okay, so there's no correlation between the one step to the next step. So then what can I do? Huh? Right, yeah, I can make product, okay, but I have to be careful that n equal to m terms are special, right? So I have to separate those terms. So I just write n equals to 1 to n square, okay. And then I have terms which are n not equal to m. And those are, because I said different steps are uncorrelated, so I can write them as this correlation can be written as product of the averages. Okay, so I can write it as Vn. Right, okay. So then this is, so what is this? 0, right? Because each of this is 0, and this is, each of this is 1, so it's just n. Okay, so this is kind of one of the most important property of a random walk. The mean square distance traveled is so the, if you think of kind of, I mean, this is really the distance traveled. This is n to the power half. Okay, so in time t, you travel kind of root of time distance. I mean, if you are moving like with a constant speed, typically you will travel a distance t, right? But here it's much slower because on an average you are not doing much. So you go only root t distance. Root t is of course much smaller than t. Okay, so okay, so this is like what is the average distance? What is the average mean square distance traveled by the random walker? And then you can ask more detailed question. I mean, so you can ask like after n steps. So let's say after 2 steps, you could have come back to the origin. You could have gone like that and come back, or you could have gone here, or you could have gone here, right? So there are 3 places you can be after n equal to 2 steps, right? So you can ask after 2 steps, what is the probability I am here? Okay, so what is the probability after 2 steps? Huh? Okay, 1 by 2, someone said 1 by 2. Okay, so 1 by 2 is right, because there are 2 processes which will lead me to this place, right? I can go like that or I can do like that. Each of these is probability 1/4. So the probability of coming here is half. The probability of being here is 1/4, because there's only one path, and coming here is also 1/4. So total probability of course has to add up to 1. Okay, so then we can generally want to ask after n steps, what is the probability I will be at various points on the lattice? Right, so this I'll call P probability that I'm at y after let's say n steps. Okay, so what is this? So this again, all of you have done. Okay, so tell me where should I stop here? And this is fine. This much is it? Okay, so anyway, this is 19. Okay, so this of course all of you have done. So you basically say that in any given realization you would have taken let's say steps, right? So in any realization, so like when I came back to the origin, there was one right step, one left step. In to reach here, there were two right steps, right? But if I take 4 steps, then I can reach here. To reach here, I have to take on total. Okay, so I can either go like this. So that's 3 right steps and 1 left step brought me here, right? 1, 2, 3 right steps and 1 left step brought me here. But I could have done 1 left step and 1, 2, 3 right steps. Okay, that's the same. Or I could have done like this and like this. Okay, so then various number of right and left steps can bring me to that point. Okay. So basically now these are the, then we basically say that the total number of steps is n, and I have the constant that I want to be at y. So right minus L must be equal to y. So this I can solve, and this gives L equal to okay, so these are the okay, this is here. So now I ask in n steps, how many ways can I take L steps to the right and R steps to the left, the other way around. So that is n factorial divided by R factorial, right? I mean, I've taken n steps. I mean, and I can, so the n steps, I can put L, 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 and R, R, or I can put L, R, L, L, R. Right. So this, both of them have 3 left steps and 2 right steps, and so the number of combinations must be this. And the probability that of each of the paths is 1 by 2 to the power n, right, of each realization. So this must be the probability that I will reach. So once I fix my y and n, then of course R and L are fixed. So this must be the probability of this that I want. Okay, so okay, so this is equal to P y of n, and now I can express L and R in terms of n and y. So okay, so this is the probability distribution of that after n steps, the walker is at various points on the lattice. Okay, so you can see that if y is greater than n, this will become 0, and y is less than minus n, also it's 0. And some other properties that you can easily verify is that p, y, n, sum from n equal a. equals to 1. Okay. I mean, how do you prove this? Is it obvious this is true? Right, yeah. So this actually, if you expand half plus half to the power n, then each coefficient is basically this, right, more or less. Okay, so, and this is of course 1. So this you can prove, and then given this distribution, of course you can find all moments, right? So so if you want to find what is the average position, then of course you just do y n sum over y, and that will again give you 0, of course, because it's yeah, and you can find y square average. It will give you exactly what you got by the other simple argument. Okay, so this is called a binomial distribution, and for this reason, okay, so now if you if you plot this function, so at this on this lattice, you can ask what does at various times what does that distribution look like, right? So at time 0, you started with a distribution which is just 1 at so I'm plotting p of yn as a function of y at various values of time, which is n. So this is at n equal to 0. So this is 1. The probability is at the origin with probability 1, right? Then after at n equal to 1, of course it looks like, so maybe I'll use a different. Okay, so at time 1, it will look like it's half here and half here, and it's 0 everywhere else, right? So probably after an odd number of steps, it can never be at even sites. So out here, everywhere is 0. After time 3, so it can be 1, 2, 3. So 1, 2. Sorry, after 2 steps. So n equal to 2, we said that it can be here with probability 1/4, so which is like that, and it can be here with probability half, and it can be here with probability 1/4. Okay, and then you can keep doing for larger and larger time, and then if you do for kind of large times, if n is large, then what you find is that this distribution will look like what? Gaussian, right? So at already it's looking Gaussian in fact. So if you do really large times, then it basically looks like, okay, it has to be normalized, but it goes to a Gaussian distribution. Okay, so let's see how that comes by. Okay, so basically to show that this is a Gaussian distribution, okay, so this will be homework mostly. So what you do is, so you have P of yn. Okay, so to show that, you have to basically use something called Stirling's approximation. Okay, so the Stirling's approximation is basically an approximate formula for this factorial, and it's given by n factorial So actually, even though it's called Stirling's formula, actually Stirling didn't derive it. Okay, so I mean, there's someone called I think D. Moivre. Do you know what he did? D. Moivre. There's some some complex analysis. He did a lot of complex analysis. So he actually derived most of it. I mean, what Stirling got is he basically added this root to pi factor. Okay, and then everyone called it Stirling's formula. Okay, so now this actually there's a very nice derivation of this Stirling's formula. I mean, so how many of you know how to derive this formula? Okay, some of you know. But this one I'll just outline the thing, outline the derivation, and then you can complete it in the tutorial. It's a very instructive example of using this saddle point method. Okay, so I mean you should really do this. So simple. Is to use the fact that n factorial can be written as this one everyone knows. Okay, so then what you can do is you can rewrite it as equals to x. So this is exactly the same. And then what I'll do is I'll take this n factor outside and put it right as minus x by n. So this is also exact, right? No approximation. Okay, so now if n is large, then there's something I mean, it's a very common thing to do in physics, is do a saddle point approximation, where you say that this function is kind of contributes to the integral at the place where this thing is kind of has the maximum value. So if you plot it, I mean, this entire integral, it might look like, I mean, so if where this has a maximum, it will be peaked, right? Okay. And you kind of forget about all this other part and just try to expand this function around the maximum point. Okay, then you'll get a Gaussian, and then of course you can do Gaussian integrals, right? So just forget the behavior of the entire function. Just try to find its behavior near the maximum point. Okay, so let's call this function f of x. And so this is what I'm plotting, f of x. Okay, and I just want to look at, because this will give the maximum contribution to this integral. So now if we do that, so you will basically get dx 0 to infinity e of n. So expand fx about the maximum. Okay, so let's say x star is the maximum. So x star, so maximum means at f prime f x star is equal to 0. That defines the maximum. It could be minimum, but here you'll find it's a maximum. So so this is then this plus right. So you just expand till this, and then of course you can write this as f of x star. And then this integral e to the power n by 2 dx. And now also you can, because you are anyway like expanding around some maximum, you can, I mean, you expect that contributions from far from this point is doesn't matter anyway. So here instead of 0, you can just put minus infinity. So this now is not exact, it's approximate, right? Because you just expanded this thing up to square and then it neglected everything else. So you get something like this. So now, of course, it's a Gaussian integral, which you can do exactly. This you can easily find where at what value of x it's the maximum. And then you just do this and you will find this formula. So this you'll do in the assignments. Okay, so then you use Stirling's form approximation out here. And then you do, so this again, I won't do the steps. I mean, okay, so okay, so you now use Stirling's formula in this, and and so this is, I mean, so this you should definitely, if you have not done it once, you should definitely do this algebra once. Okay. I mean, so at the end of the process, you get this. Okay, so this formula is valid. I mean, actually, so when you do this, I mean, when you do this this step, so this is also a tutorial. When you do these steps, what one other thing you have to use is that this formula is actually valid if you are looking at y shouldn't be of order n. Okay. So for example, I mean, you know that for the exact process, I mean, the probability is strictly 0 after y equal to n, right? But this, of course, gives you a finite probability, right? It's extremely small for large n, but it gives you a finite probability. So this formula is not really valid at really large. So this is valid for y on the scale of root n. In this range, where actually the most of the probability is concentrated, it's extremely accurate. Okay. But and then of course mostly you don't care about the large deviations, but that sometimes you might be interested in large deviations. Okay, so okay, so I just wanted to mention one other point that this, I mean, this formula is actually extremely accurate. Okay, so it's good to know how accurate it is. So if you do like n equal to 5, so n factorial is what, 120. Okay, and the Stirling's gives you like 118. Okay, so this is already at n equal to 5, it's extremely accurate. Okay, so even though it looks approximate, it's and as you go larger, it becomes almost exact. Okay, so now we have got this, and now maybe we'll try to see. So this is still a probability like a probability distribution, and now we want to. It almost looks like what Sanjib got in his previous lecture, but it's still not exactly the same. Okay. So what he had got was P of so here, I mean, this t is time like n, and this is space. So it looks very similar. But how do we exactly get this? Okay, so for this you have to do one more step, and basic idea is that one now has to go to the continuum limit. Okay, so. So right now we have a probability distribution, which is like it's a non-dimensional number and at each site you have some value. Okay, so in fact, one thing you notice at that alternate site is the probability is 0. Okay, so at an even time, if n is even, then you'll get some probability at the origin and 0 at the next time, and maybe something here, and then 0 at the next site, and then something 0 and some distribution like that. And now what you say is that you want to go to a continuum limit. So then you have to say that your each lattice site has some size. So let's say this distance is a, the lattice spacing is some a, and then you want to go to continuous time. So you say that each time step takes some time tau. So we'll just say t equals to, this is the discrete time step, but now if you want to go to a continuum time, you write t equal to n tau, and y is equal to y times a. So this is continuous time and continuous y. Okay, and then how do you get p of yt? So p of yt is basically equal to, so let's say p of y n Okay, so by the way, this is, I mean, kind of like a physicist derivation, right? Okay. Which one? Oh, sorry, this I'm plotting P of y at some time n. So this is y. After, that's what I said, right? After, let's say after, if you take 2 steps, you can never be at 1, right? At site 1. That's clear, right? That's clear. So that's if you take 4 steps, you can also be never at site 1. Because if you take an even number of steps, you have to be at an even site. And if you take an odd number of steps, you have to be an odd number site. So I'm saying, assume n is even, then at every odd site, the probability is strictly 0. And it's non-zero only on even sites. Right? Okay. Yeah, okay, so I was saying this is like it's what's called a physicist derivation. Okay, so if you ask a mathematician, they of course won't like it. And they'll write maybe, I mean, they will have a 20-page proof of the same result. So, yeah, so actually a lot of things physicists do, I mean, they can get the right result using some very, so you should be the kind of, you shouldn't worry too much about whether this is justified or not and so on. Okay, then of course, I mean, the good thing is physicists typically also do simulations. You can easily check that, I mean, also you can compute, right? And you can check that it works. Okay, and then of course, like quite often, sometimes physicists prove something and then mathematicians can provide a rigorous proof, which is also important. Okay, so now you have to understand this result. Why did I divide by 2a? Okay, so first of all, this quantity is a probability density. Okay, so this has dimensions. Okay, because like if you see the way it was, I mean, it was defined as an so it's a continuous function, and its normalization is this, right? So for the discrete case, I said it had a property, okay, somewhere there, that the sum of all the y's is 1. Okay, and p is a dimensional probability, right? It's a dimensionless number, but this is a probability density, right? It has dimensions of 1 by length, right? So so obviously I have to divide by distance to get yeah. And so what does this give? This gives me the probability. So py into dy gives me the probability. That is a dimensionless number. Okay, so py into dy, that's a dimensionless number, and that gives me the probability that the walker is between y2, y plus dy. Right. So now, basically, to go to this continuum limit, what I have to do is I have to imagine that there's some y and y plus dy. But this dy is really includes large number of lattice points. Okay, and I have to sum up over all those points and then find the total probability and divide by the distance. Right. Okay, so in this case, I mean, the minimum distance you have to divide is 2a because, I mean, alternate sites are 0 probability. Right? So if you do an average, I mean, like this size is already 0. So you have to, so that's why you get a factor of 2. Okay, so if you do this now, so P of, you can immediately write what P of yt is. So it becomes, so P of yt is equal to, so I divide by 2a, so I can then get 1 over okay, so now this is, so, and now I re-express y and n in terms of this t and y. So then I'll get 1 by 5. N is t by tau, so a square by tau. And then y is again y square. Okay, so I'm just replacing y by small y by a and capital N by small t by tau. Okay, then we get this, and now let's define okay, so now since we know that y square is equal to n, and so if you write it in terms of y, we know that y square is equal to n, and you divide by tau and multiply by tau. Okay, and then from the continuous process, we know that the diffusion constant is defined as 2 dt. Right? So therefore, this quantity a square by tau can be identified with the diffusion constant. So diffusion constant is just a square by 2 tau. Okay, so you replace a square by tau by 2d, and then you basically get back this result. Okay, so this random walk is the same guy, which is like what Sanjib talked about, the Brownian particle, right? I mean, there it was moving in, I mean, in continuous time and continuous space, but this discrete process basically describes that. Okay, so this random walk actually has a very interesting history. I mean, it was first introduced in, I think, maybe so around 1900, around 1900. So there was, I think, a botanist called Pearson, and he was interested. He was not botanist, I guess zoologist, because he was interested in movement of mosquitoes. Okay. So he was like basically worried about, like, if you have large concentration of mosquitoes at a place, how does it spread? That's I mean, obviously interesting question. And so then he asked the question, like, if I write a simple model for what the mosquito does, which is like, so his model was, he defined a two-dimensional model. Okay, so mosquitoes, I mean, roughly if you see from top, it looks like two-dimensional. Right? So his model for mosquitoes was, it starts from some place and chooses a direction randomly and moves for a finite, let's say, some step, okay, some distance. And then it chooses again another direction randomly and moves like that for the same distance but in a random direction. And then again it chooses a direction randomly, and so this is the XY plane now. Okay, and then it keeps doing this. Okay, so every time it chooses a random direction and moves like that, again moves random, and okay, so it keeps moving like that. And then he basically asked the question, like after time, after n steps of this mosquito, which is like time, each step takes some time tau. I mean, typically, how far does the mosquito travel? Okay. So this is a question. I mean, that those times you can write, like you can ask a question and put it in a journal. Okay. So he put it in the journal Nature as a question, and then this I think Raleigh, he actually answered the question, and he said that he had actually solved this problem while trying to understand diffusion of sound in random media. Okay. So sound is like waves, and then it also, if it's a random medium, in some sense, it does a random walk. Okay. And so he had actually exactly answered this question, and he had the solution for the what is the probability that after time t, it's at some position xy at the time t. So here's already an exact solution. So that's the how this random walk problem. I think probably that was one of the first times this question was posed and answered. Okay, so I just wanted to say that random walk is actually used in, I mean, like huge number of fields. It's mathematically beautiful and has lots of physical applications. Okay, so now what we'll do is uh, again try to solve, okay, so we'll again solve it in different ways of the same problem. Okay, so for the Brownian particle, what you saw is that P is given by this, and the way you obtained is that you started from a diffusion equation, right? You somehow you obtained a diffusion equation. And you solved it to get this distribution, okay? But in this case, we have done it in a slightly, I mean, different way using probability, like combinatorial methods and so on. Okay, now can you actually also do the same thing out here, like start with the diffusion equation? So one can exactly again write the corresponding thing in for the lattice problem. So for the so that's kind of called a master equation, maybe. I mean, or so. Okay, so this, I mean, is easy to get. I mean, basically, so you have a lattice, and let's say at some time n, you are at some point x, right? And so it's exactly like the way you derived this equation. So if you are at time, if you are at x, and you basically ask where all could I have come from? Okay, and then it's clear I can either come from x minus in the previous time step. I either am x minus 1 or x plus 1, right? So then the equation is given by P, probability that I'm at x at time n must be the probability that I was at x minus n or x plus n at the previous time step times what is the probability given that I'm at x minus 1, what is the probability I go here, right? That's half. So I should multiply by half. And then there's another process which contributes, which is the probability that I was at x minus 1 in the previous time step. Okay. So this is like the discrete version of this equation. So here time is changing from n minus 1 to n. So it's a discrete time equation. Okay, and then of course you can immediately see that this and this are related if you just if you subtract this, then okay, this you can see, is it? No. Maybe I shouldn't go there. So I have this equation P of xn, and I want to, now I just want to show how do you get the continuous equation, diffusion equation starting from the discrete equation. So of course you have to subtract the previous time. So you want to get something like del t. So you time derivative is like n minus 1, and so on the right hand side you get half. Right, so this is clear, I hope. Okay, so the object is actually sometimes called the discrete Laplacian. I mean, you can write it like that. So it's, I mean, just like you had, so the continuous Laplacian is in one dimension is del 2x. So this is the discrete version of that, and you can easily see why. I mean, so now if you, sorry. No, so sorry, what was your question? Oh, this was your question. Okay, sorry. Yeah. Okay, so yeah, so this I got exactly from there, right? I just subtracted pxn. Okay, so now you can see that this is I mean, okay, so now if you just replace, do the same business, x equal to then take the limit a going to 0. So if you do this and just convert just do Taylor expansions, right? For example, P of x plus 1 n plus 1. This goes to P of x plus a t plus tau. And then what you should do is just expand this. Okay, so P of x t plus del p del x a plus half a square and so on. So if you just do Taylor expansions, then you can easily see that you get this equation. So again, I won't do the steps. This is quite, I think most of you might have seen this already. But you should note that you're taking the limits in a special way such that this is kept constant. So this is called the diffusive scaling limit. Okay, so this is if you go to it, so this is where you go to the continuum approximate limit. But now you can ask, I mean, given the discrete difference equation, so this is a partial differential equation, right, which tells you how the probability distribution evolves in time. Okay, so it's very similar to Schrodinger's equation, right? Like it's except there's no I. So if you put an I here, it's exactly Schrodinger's equation, right? Okay, so then this is the discrete version, and you can ask, can I actually solve this exactly? Okay, so instead of looking at the this equation, can I actually solve this exactly? So we already know the solution, right, because of using these combinatorial methods. But is there some other way to solve this difference equation? So okay, so how did we solve the diffusion equation? What was the, how did you solve? Fourier transform, right? So we'll do kind of the equivalent version of Fourier transform on the lattice, right? So then what do you do? So this given this equation, so solving. Okay, I've changed y to x. Okay, so I'll go back to y. Uh, Okay, so if I want to do now again like Fourier transform, what should I do? Like on a lattice, instead of continuous x, I have a lattice x, right? So I should do like Fourier series kind of, right? So basically, I'll define a function p tilde. So there, in the continuous case, I defined p tilde k equals to right. So now, of course, I mean, similarly, I'll try to define a Fourier, so p tilde and maybe theta t is equal to. So I don't have a continuous x, so so I just do a Fourier series. Okay, and I put e to the power I. Yeah. Okay. This one is not enough, is it? This one is not good. Okay, this one is okay. Okay. Sorry. P of, okay, so this is in continuous. And now time is also discrete, so in. Right, so I just define a Fourier series instead of Fourier. I guess this is called Fourier transforms. This is called Fourier series, right? But basically this okay, and then this I can of course invert p of. Okay, so this is I'm changing the lattice position to an angular variable, and time is still kept unchanged. So this is exactly what we do in the solution of the diffusion equation. Okay, so if we do this, then what do we get? So given this equation, I just have to multiply by e to the power I theta y and sum over all y. Right? So so I. And then sum over all y. Okay, and so then what we get is p. Okay, so if you multiply by e to the power I theta y, so there's a y plus 1, so you should take theta. So basically the idea is you have e to the power I theta y times p of y plus 1 n, sum over all y. Right? So you can put a y plus 1 here and take out e to the power minus I theta, and then this just becomes, now you can change y plus 1 to y, right? Because sum over all y. So you just get an extra factor of minus I theta. So this is e to the power minus I theta by 2. Okay, so uh, okay, so so now it's easy, right? So the in the theta variable, the distribution at time n is related to the distribution at n minus 1 just by a simple factor. So now I can write so finally what I want to do is I want to write the distribution at time t given the distribution at time 0, right? So I have to relate this to the p at time 0. So this I can just iterate, and then I get p tilde theta n equals to cos theta to the power n times p tilde. Right, this is clear. Okay, so again, I just want to remind in the continuous case, this step is equivalent to writing e to the power minus t square t p tilde. Right, so these are exactly equivalent. Okay, now so now what is p theta 0? P tilde theta, what is this? Huh? It depends on initial condition. So initial condition, let's say I start from the origin. So then what is it? 1. I should use basically, yeah. So I should use this, right? I know this at time 0. So at time 0, this is, I said this is delta of y0, right? So this is at time 0, this is discrete Kronecker delta y0. So then this summation gives us 1. Right? So that is here. So this is actually 1. For this initial condition, of course, if it's a different initial condition. Okay, so therefore p tilde theta n and now I can go back and then I have the solution. So p of okay, so this is the final solution. If we do the integral, what will we get? I mean, is this doable integral? Huh? I mean, what should we get? I mean, because we know the answer already, right? I mean, we're doing this just to read it right, but we know the answer. I mean, the answer is what? Not Gaussian. No, it's not Gaussian, okay? You shouldn't say Gaussian. That's the entire point. It's the Gaussian is an approximation. But this is exact on the lattice, right? So it's not Gaussian. It's the binomial distribution. So the answer is, of course, 1 by 2 to the power n. Okay, so it's already okay. So it's maybe it's not obvious. I mean, how to get the simplest way to see that is like I can write cos theta as e to the power I theta plus e to the power minus I theta by 2, right? And then when I do the integral, I can do the binomial expansion, and then of course only one term will contribute in this summation, right? Because I use the property that it is for I theta x d theta minus by 2 pi. I mean, what is this? This is delta of x0. Right? So using that property, you should be able to easily see that this. Okay. So just make the, write this as e to the I theta plus e to the minus I theta, do the binomial expansion, and then in the expansion you easily see that only one term contributes and gives you this. Okay, so this of course is not a very clever way of doing this problem. This was much easier to do the other way. But yeah, I mean, this is useful because in some other cases this will be useful. So that's why we are doing this. Okay, so okay, so now I'll do a slight variation of this random walk, where we saw two cases where like one is discrete time, discrete space, and then we saw continuous time, continuous space. But you can also do a diffusion on a lattice in continuous time. Okay, so how do you get that limit? Okay, so uh, okay, so the way to derive that limit is like you want to take the limit where it's still a lattice. So, I mean, here I took a particular limit, like a going to 0, tau going to 0, and this thing going to constant. So I don't want to take the limit a going to 0, but still want to go to the limit of continuous time, right? So it's like I am you have a lattice and you are with some rate you are moving to the next side, with some rate you are moving to the left side and so on. So the time is continuous and you want to write in terms of rates. That is something we always do, right? We write rates. So how is that related to this? How can you get that from starting from the random walk? Okay, so I'll just talk about this process. So okay. So in this case, actually, like if you, with the random walk that I wrote, it's difficult to arrive at this. So we have to change it slightly, the random walk model to get this kind of a limit. Okay. So the process we'll now consider is a random walk where, okay, so again, yn plus 1 is equal, yn minus 1 plus zn. But now we say that zn equals to, let's say 1 with probability p by 2 and equals to minus 1 with probability p by 2 and is equal to 0 with probability okay, so with some probability I go to the right, some probability I go to the left, but there's a probability I just do nothing. So this is a slightly modified version. Yeah. Right, yeah. Which theta? No, theta is like k. I mean, physically it doesn't mean anything. I mean, k is like just a Fourier transform. In Fourier space, I mean, whatever, but it's not, I don't know what it means. I mean, of course, like in terms of, like if you have a function, the kth command, I mean, it just tells you that a particular frequency, I mean, what is the probability of that? I mean, but it's not, for example, p tilde kt, this is not a distribution. Okay, so if you integrate dk, this is not 1, right, unlike pxt. So it's not a, it doesn't have a physical interpretation. Okay, so now for this, we'll write our okay, so what is y average for this? Is 0, obviously, yeah. Okay, and what is y square average? NP, is it? Okay, so it will be Zion square average, so that's 1 and yeah, it's NP. Okay, so now let's write the P of the evolution equation, P of y at time. Okay, and then I'll have one more term. What is it? Yeah, staying. So what is the probability? So what is the term I should write? And then? So this is yeah. Okay, so okay, so now I just want to go to keep y still continuous and take time continuous, right? So then I want to define n equals to okay, so then I want to find py is equal to so if I subtract, so this term goes away, so I get basically p by 2 okay, and then I have to divide by tau. So I want to get a continuous, like because t is now continuous, so I want to write del p del t. Right, so then I divide here by tau. Okay, and then now there's no a or anything. Okay, so I don't have another. Okay, so now I want to take limit tau going to 0. So this will of course give me del p del t. So the left hand side gives me del. Now let's call it del p. Y is still discrete and time is continuous. So del t. And this one, I'm taking tau going to 0 limit, so this will of course blow up unless I also take the limit p going to 0. Right? So in that limit, I'll call this p by tau. Okay. Or p by 2 tau, let's say. Rate. Okay. So okay, so I get this thing. Okay, so this is just R P. Okay, so now it's a rate equation, and you can easily like physically one way of saying this is that the rate at which the probability at a site. So this is a lattice. The rate at which the probability at a site changes is because their things are coming in with some rate and from the two places, and then just from this place they're going from both directions, right? So minus 2r. So this is the loss term and this is the gain term. So this is like when you write rate equations, you complete like that's how you. Okay, so here it was important that you actually introduce this parameter p, right? Because for the usual random walk, p is 1. right? So then, of course, P is not going to zero limit, so you could never have got this continuous time random walk. So, I mean, yeah, so in this, if you want to really, for example, do a simulation of this process, you have to define a random walk like in this precise way. Oh, sorry, this is what I defined as the discrete Laplacian. The delta was, I called this, okay, so this should be called delta of t. I mean, just like on the continuum, the Laplacian is defined as del x square, right? So for a discrete, I mean, so if I write del t, this means del x t, right? On the lattice, this means if I write del t at, let's say, x, this by definition, it means p of x plus 1 minus 2 of px plus p of x minus 1. I mean, see, this is like taking two derivatives, right? That's clear, right? Because it's like p of x plus 1 minus p of x, and then minus p of x minus p of x minus 1. So this is one derivative, and then this is second derivative. So that's, so it's, I mean, so usually it's called the discrete Laplacian operator. Okay, so that's why I wrote it like that. And so this is just the explicit, this is the same thing explicitly. Yeah, but you're also taking, see, you're looking at time is finite. Okay, so each time step is tau going to zero limit, but you're taking a large number of steps. Okay, so in that limit, you'll eventually move. Because even though, so that's the special limit. Like even though the hopping probability is going to zero, but then in the in a large number of steps, of course, you will move. And so this one then becomes like, so here if you divide by tau and multiply by tau, see that's what, here also it's clear, right? So even though you are taking this going to zero, this going to zero, this is finite, but then this is also finite. So this is t times rate. That's the average. Okay, maybe I put a 2 here, so it should be. How much time? 5 minutes. Okay, so I mean, where is this is the question. Okay, so now, so how would you now solve this equation? If we want to get a, like, similarly, the way we solve this, how would we solve this equation? No, I mean, Laplace transform means in time. No, I mean, right, yeah, see, I mean, this is almost the same equation as the previous one. Their time was discrete, but time we don't care about, right? We have only, the space is still discrete. Time has become continuous. So we can do exactly the same thing that we did, right? So we just multiply by e to the power, the same, exactly the same thing. So because we had, when we solve the diffusion equation, it's a Fourier transform in time, in space, right? Not in time. So we are always doing transforms in space, not in time. And the reason we are doing is that the time part is simple. The space part is kind of complicated, right? You have this y plus 1, different sides are coupled. But once you go to the Fourier basis, then things become decoupled, right? That's the trick. I mean, see, in theta space, each theta is connected to just one theta. Right? In y space, like y is connected to y plus 1, y minus 1, so it's difficult to solve. But once you do the Fourier transform, it becomes. So here also you do exactly the same thing. And so then you define p tilde y theta t. y, right, yeah. So then the equation you get is del p tilde by del t is equal to r. So what will this be? This cos theta, just cos theta, and right, times p tilde theta. And so now what is the solution of this? Huh? No, what is the solution of this equation? Oh, sorry. What is the, see, I said, like if I plug it into this equation, what is the equation I'll get? Is this right? Okay, maybe this is wrong. Okay, so what is the equation? From here, what will, if I do this transformation, what will I get here? Okay, cos theta. And there's a minus 2, right? So there's a 2 cos theta minus 1 maybe. Right, okay, so and then I just take the minus outside and the 2 outside. Okay, I think this is right. Okay, so this, now what is the solution? It's just the same as the diffusion equation solution, right? So it's just e to the power 2r 1 minus cos theta t and t tilde theta at 0, and this is again 1. So this goes, and so our final p of y at time. Okay, so this is the final solution. Okay, so I think it's okay. So I mean, if you take long times, actually, you can see that at long times, small theta is important, and then you can just write it as theta square by 2, right? So then you pretty much get back the diffusion, the Gaussian distribution. But if you exactly plot this, then this will be completely different. I think this can be done exactly with some Bessel function. Okay, so y is discrete. Yeah, that's right. So that's what I said. Like, if you have a see, like it's like when you define a Fourier series, right? What do? You take, you define. I mean, you have a function on a lattice, right? And you define something, theta, right? Where theta is, of course, a continuous variable, right? So that's why the inverse, when you write inverse Fourier series, that's in terms of an integral, right? T theta. So n is discrete, but theta is continuous. Right? So I'm just doing Fourier series actually instead of Fourier transforms. That's the trick involved in solving. Okay, so basically in this class, I mean, we talked about the 1D random walk, and we introduced some techniques of solving this equation in like discrete time, discrete space, and continuous time, continuous space, and so on. And okay, so in the next class, we'll basically talk about like results in higher dimensions. And then this introduced something called generating functions. I mean, actually, this is already, in some sense, these are generating functions. Okay. So this is actually, I mean, generating function is actually more or less like I said, a Fourier transform or a Laplace transform. So these are some sort of generating functions. But we'll use this generating function to understand this polya problem. Okay. So, I mean, so the question basically will be, okay, so in the next class, what we'll do is generalize to higher dimension. And 2 is this polya problem. Okay, so this is a really interesting question. Okay, so basically you're asking, I mean, you are, so this is some lattice. Okay, and this is the origin. And so random walk is like it goes like that. Right. So then, of course, if it's in infinite space, right? So then, what is the probability you'll ever come back? Right. So that's. I mean, so what do you think? Okay, so all of you know the answer. So okay, so but anyways, I mean, if you don't know, then it's not okay. So the answer is that if you are in 1 dimensions, you will come back with probability 1. Okay, if you are in 2 dimensions, you come back with probability 1. But if you are in 3 dimensions, then you come back with a smaller probability. Okay, so you may not come back, which is kind of physically obvious, right? I mean, because in 3D there's so much space. You just keep walking, you go somewhere. In 1D there's not much space, so this likely you might come back. Okay. So then, of course, you can ask other questions like, on an average, how long does it take? Okay, so here, I mean, like maybe after 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 step you came back, right? In another realization, you might take like, you might take 100 steps and then come back. So come back for the first time. Okay, so you might ask on average, how much time does it take to come back? So then, of course, the answer is in 1D, even though you come back with probability 1, the average time taken to come back is infinite. And that's true even in 2 dimension. And in 3D, you come back with a smaller probability, but the average time is also finite. So there are some very interesting results. Okay, so this we'll try to understand this. So this is called the Polya return time return probability problem, and we'll use this generating function technique to understand various results. So there again, we'll use some of this that results that we're obtaining. Okay, so some of these results. You can write it either in this form or this form, but it turns out that this form is actually more useful when you construct things like that. So that's why these are kind of useful. Okay, so any questions?